Have you ever had that feeling like you really want to get a handle on a complex idea? Really dive in and understand the nuances without getting bogged down in all the technical stuff.
Oh, absolutely. I think we all have those moments.
Yeah, and that's exactly what we're doing today. Taking a concept that seems simple on the surface and digging deep to see what lies beneath. We're diving into Albert Einstein's famous statement, God does not play dice with the universe.
It's a quote that's so simple yet so profound, right? It really opens up this huge discussion about how the universe works at the most fundamental level.
Exactly. And to help us unpack all of this, we have some amazing material in front of us. We've got excerpts that look at Einstein's quote through the lens of chaos theory, along with some explanations of what it really meant in its original context.
And let's not forget about Einstein's deep belief in a universe where everything was predictable, and how that clashed with the idea of randomness that came with quantum mechanics.
Oh, for sure. And we also have some really interesting thoughts from Ian Stewart's book, Does God Play Dice?, to draw on. So our mission today is to take all of this information, to break it down for our listeners, and to really understand what Einstein was trying to say and why it's still relevant today.
A tall order, but I think we can do it.
I think so too. So there are really two main ways we'll be looking at this quote. First, we'll dive into Einstein's firm belief in a universe governed by laws and how that contrasts with the fundamental uncertainties of quantum mechanics.
Right. And then we'll look at how chaos theory comes in and adds even more layers to this whole debate.
It's going to be a fascinating journey. But first, let's start with Einstein's perspective. What was it about the idea of a universe ruled by chance that bothered him so much?
Well, if you think back to the scientific thinking in the 19th and early 20th centuries, the dominant view was this idea of a clockwork universe.
Like everything was a perfectly tuned machine.
Right. Exactly. Yeah. And Einstein was a huge believer in this framework. He was completely convinced that the universe operated according to absolute laws, cause and effect. Yeah. Everything had a definite cause leading to a definite effect. There was absolutely no room for chance or randomness in his view of the cosmos.
So for Einstein, it was all about knowing the starting conditions, right? Like if you could somehow know everything about a system at a specific moment, you could, at least theoretically, predict its entire future with perfect accuracy.
Exactly. And this idea really comes through in his famous quote, especially when you think about his disagreements with the emerging field of quantum mechanics. Remember that letter he wrote to Max Born?
Oh, yeah, the one where he said, you believe in a God who plays dice, and I in complete law and order.
Precisely. And that quote really sums up his deep discomfort with the idea of probability that was being uncovered in quantum mechanics. The very idea that fundamental events like the radioactive decay of an atom happened by chance rather than some strict underlying law was really troubling to him.
It almost sounds like this wasn't just a scientific debate for him. It was like a philosophical or even an emotional rejection of the idea.
I think that's a great way to put it. He just couldn't accept the idea of randomness being baked into the very fabric of existence. In fact, you could argue that his entire scientific career was driven by this deep belief in an underlying order. This belief in a hidden structure is actually what drove him to spend so much of his later years searching for a unified field theory.
He was convinced that there had to be a single deterministic framework that tied all the forces of nature together, right?
Exactly. And for him, this wasn't just a scientific pursuit, it was a reflection of his core philosophical beliefs. He felt that quantum mechanics, with all its talk about probabilities, was just an incomplete picture. He thought there had to be some hidden variables that, if we could only find them, would restore his deterministic view of the universe.
So it wasn't that he thought quantum mechanics was wrong in its observations, but rather that it was missing a piece of the puzzle, a piece that would ultimately reveal a deterministic reality underneath it all.
That's a really important distinction to make. He definitely recognized that quantum mechanics was incredibly successful in explaining a lot of phenomena, but he still maintained that its probabilistic nature was a sign that we hadn't uncovered the full story yet. He just couldn't accept that the universe at its most basic level was governed by chance. Now, to really understand where he was coming from, I think we need to spend a little time talking about quantum mechanics itself.
Okay, so quantum mechanics. This is the physics of the really tiny, the realm of atoms and the particles that make them up. And what makes it so different from classical physics is that the rules we're used to in our everyday world just don't apply at that scale.
Right. Instead of being able to say with certainty, this particle will be at this location, you're suddenly dealing with probabilities. You can only talk about the likelihood of finding a particle in a certain place. It's a completely different way of looking at how reality works.
So The very nature of quantum mechanics introduces this element of uncertainty, right? It's not just that our instruments aren't precise enough, it's that the universe itself is inherently fuzzy at that level.
Exactly. And this isn't just a minor quirk. It's woven into the very fabric of quantum mechanics. Think about wave-particle duality, for example. This is the idea that a single particle can act like both a wave and a particle, which brings in a level of fuzziness right from the start. And then you have the Heisenberg uncertainty principle, which says that there are fundamental limits to how precisely we can know certain pairs of properties of a particle at the same time, like this position and momentum. This isn't just about our ability to measure things, it's about the limits of knowledge itself.
So even if we had perfect measuring tools, there would still be an inherent uncertainty in the universe at that scale. It's like the universe itself is playing dice, right?
Well, that's the big question, isn't it? And this leads to some pretty mind-blowing philosophical questions. Does the probability we see in quantum mechanics just reflect our lack of knowledge, as Einstein believed, or is it truly a fundamental part of reality? Does the very act of observing something change the reality we're observing? These are the kinds of deep questions that come up when you start talking about the probabilistic nature of quantum mechanics.
And these were the questions at the heart of the famous debates between Einstein and Niels Bohr, weren't they?
Oh, absolutely. The Einstein-Bohr debates are legendary in the history of physics. You have these two intellectual giants who had completely different views of how the world worked. Bohr was a central figure in developing the Copenhagen interpretation of quantum mechanics, which fully embraced this idea of probability being a fundamental aspect of reality. He argued that at the quantum level, the only thing we can talk about is the probability of different outcomes. Trying to impose our classical deterministic view onto that realm just wouldn't work.
So Bohr was basically saying, this is how the universe works at its core. Probability isn't a sign of our ignorance, it's just a fact of life down here.
Exactly. Bohr believed that the kinds of questions Einstein was asking about hidden variables and a deeper deterministic reality were ultimately unanswerable and maybe even meaningless within the framework of quantum mechanics. As far as he was concerned, the theory was incredibly successful at making predictions about the quantum world, and that's all that mattered. And despite Einstein's brilliant thought experiments, which he used to try and find flaws in quantum mechanics, Bohr and his supporters always had a counter-argument. Einstein never really accepted the Copenhagen interpretation, but he also never managed to disprove the inherent probabilistic nature of quantum mechanics.
It's amazing to think that two such brilliant minds could look at the same evidence and come to such different conclusions about reality. And it brings us back to Einstein's famous quote. It wasn't just about a scientific preference, was it? I mean, his choice of words, "God does not play dice," seems really significant.
That's a great point. It's important to understand that when Einstein used the term God, he wasn't necessarily talking about a personal God in the traditional religious sense.
More like a metaphor for some kind of ultimate cosmic order.
Exactly. For Einstein, God often represented this idea of a fundamental order, an underlying harmony in the universe. He had a deep respect for the elegant and consistent laws that he saw governing the cosmos.
So when he said God does not play dice, he wasn't making a religious statement, but expressing his strong belief that the universe operates according to a deep, underlying order, not random chance.
Absolutely. In fact, the material we have here mentions that he was quite fond of Spinoza's pantheistic view, where God is essentially the universe itself in its inherent lawful structure. And while he was certainly critical of the probabilistic interpretation of quantum mechanics, he never totally rejected the theory itself. He just believed it was incomplete, that there had to be this deeper deterministic layer that we hadn't found yet.
It's like he just couldn't let go of the idea that there had to be a more elegant and deterministic explanation hidden beneath the randomness of quantum mechanics. Now, let's fast forward a few decades to the emergence of chaos theory. How does this newer development change our perspective on this whole debate about determinism versus randomness?
This is where things get really interesting. Chaos theory really gained momentum in the latter half of the 20th century. And what it showed is that even systems that are governed by perfectly precise, deterministic laws, the kind Einstein loved, can still behave in ways that seem completely random and unpredictable. The key to understanding this is something called sensitivity to initial conditions.
This is the butterfly effect, right?
Exactly. The idea that even the smallest change at the beginning of a process can lead to hugely different outcomes down the line.
Like a butterfly flapping its wings in Brazil, causing a hurricane in the Atlantic.
Exactly. And what's amazing is that it seems paradoxical. You have these perfectly deterministic rules, but they can lead to outcomes that look completely random. And this is where Ian Stewart's book, Does God Play Dice? The New Mathematics of Chaos comes in. The book dives into this very idea that what we often see as random chance might actually be the result of very complex but still deterministic rules. It's like the dice are loaded, but the mechanism is so complicated that we can't predict how any individual roll will turn out.
So it's not that there's no order, it's just that the order is so complex that it looks random to us.
Precisely. And Stewart argues that chaos theory is forcing scientists to rethink some of Einstein's fundamental assumptions. In fact, the material you provided gives some great real-world examples of where chaos theory has been applied. Turbulent fluid flow, the unpredictable reversals of Earth's magnetic field, irregular heartbeats, the weather, all these things that seem so chaotic on the surface can actually be modeled and understood using deterministic chaos.
It's mind-blowing to think that something as seemingly random as a dripping faucet or fluctuations in insect populations might be governed by underlying mathematical equations.
And one of the fascinating things about chaos theory is how it changes our understanding of geometry. The familiar shapes of circles and squares give way to these infinitely complex patterns called fractals when you start looking at chaotic systems. This incredible complexity emerging from relatively simple rules is really important. It suggests that maybe the strict divide that Einstein saw between randomness and determinism isn't so clear-cut after all. Maybe, as our text suggests, this metaphorical God can both play dice by setting up these incredibly complex initial conditions and simultaneously create a universe governed by laws.
That's such a powerful image. So what chaos theory shows us is that order itself can generate its own form of chaos. It sounds like our understanding of both order and chaos has come a long way since Einstein's time.
Oh, absolutely. That excerpt we looked at earlier talks about how history and scientific understanding tend to move in these cyclical patterns, like a spiral going upwards. We started by seeing nature as unpredictable, controlled by the whims of gods. Then the scientific revolution came along and revealed all these regularities and laws, leading to the idea of a clockwork universe. Quantum mechanics then challenged that view by introducing randomness at the most fundamental level.
And now, with chaos theory, we're seeing that even within systems governed by precise laws, there can still be this inherent unpredictability. It's almost like we've come full circle, but on a much higher level of understanding.
Exactly. And the real question now, as our source puts it, is not so much whether God plays dice, but how he does so. And this highlights how chaos theory changes our whole understanding of prediction and the repeatability of experiments. What we thought was simple can turn out to be incredibly complex. And what seemed random might actually be following relatively simple rules in a very intricate way.
It really makes you rethink what predictable and random even mean. And our source material even mentions how these ideas have implications beyond physics, with theologians and philosophers grappling with these concepts of chance, determinism, and divine action.
Absolutely. Theologians have been exploring how the ideas of uncertainty and emergence that come from quantum mechanics and chaos theory fit into different ideas about God and divine providence. There's a whole spectrum of viewpoints, from strict theological determinism, where everything is part of God's preordained plan, to more nuanced views that incorporate free will and divine action within a framework that also allows for chance. Process theology, for example, sees God as actively involved in the universe that's constantly changing, where chance and novelty are important parts of the process.
And what about in philosophy? How have these ideas been received there?
Well, in philosophy, there's just as much diversity of thought. Determinism as a philosophical concept has been debated for centuries, and these new scientific developments add even more layers to that debate. Existentialism, which emphasizes human freedom and responsibility in an uncertain world, resonates with the unpredictability highlighted by quantum mechanics and chaos theory. It all goes to show how these seemingly abstract scientific concepts really connect with our most fundamental questions about existence, causality, and the nature of reality itself.
It really is all connected, isn't it? So let's wrap things up for our listeners. We've seen how Albert Einstein, with his deep belief in a deterministic universe, resisted the probabilistic nature of quantum mechanics. His famous quote, "God does not play dice with the universe," perfectly captures that conviction. But then, as we learn more about the universe, chaos theory came along and showed us that even seemingly simple, deterministic systems can behave in ways that look completely random because of their sensitivity to initial conditions.
What's really fascinating to think about is that even though Einstein was specifically concerned about quantum mechanics, his quote ultimately reflects a deep belief in a fundamental order underlying the cosmos. His specific vision of that order, might have differed from the quantum mechanical view, and chaos theory has added another layer of complexity, but his core intuition about a meaningful structure to the universe still resonates today.
And the debate about how chance and necessity interact in our universe continues to be a crucial area of both scientific and philosophical inquiry. It really makes you wonder, doesn't it? Could there be hidden, complex rules governing even the most seemingly random phenomena? Maybe that's something for you, our listener, to think about. Where else in your own life or in your areas of interest do you see this interplay between order and chaos playing out?
It's a question that could keep us all thinking for a long time.
Indeed. Thanks for diving in with us today. It's been an incredible exploration.
My pleasure. Until next time.
See you then.
Guys, see you in another podcast. Don't forget to subscribe to our channel.